In this recording, we'll work a few more momentum problems or questions. Okay. In this case, we have a block of mass m that's going to break into two different blocks. That's going to explode into two different blocks, m1 and m2. And they label the velocity of block m1 as v1, the velocity of block 2 as v2. And it is asking which block has a larger momentum after the collision, knowing that m1 is equal m over 4, it's a fourth of the mass here, and m2 is 3m over 4, which is 3/4 of the mass. Which block has a larger momentum? Of course, here, what do we know about the momentum before? There is no motion. The momentum before is 0. So the momentum after should be equal to 0. Now, what's the momentum after? The momentum after is going to be the momentum of block 1 plus the momentum of block 2. And it is equal to 0, meaning that the momentum of block 1 is equal to minus the momentum of block 2. So they are equal, just opposite in direction. So which has the larger momentum? Neither. They have equal momentum. Equal magnitude of the momentum. Which block is going to have a larger velocity? Now that's a different story. What's P1 equal to? P1 is going to be equal m1 times velocity 1. And what's P2 equal to? P2 is m2 times v2. Now, v1 then is equal to p1 over m1, and v2 is p2 over m2. Now, since p1 is equal to p2, we have the same value here, but I'm dividing this one by a smaller number than this one. So when I divide the same thing by a smaller number, I get a larger value that tells me that v1 is larger than v2. Okay, now, here is another example. So we have an astronaut, someone out in space, essentially stuck out in space. So to move back to the space station or the shuttle or whatever, he throws a 1 kilogram anvil at a speed of 15 meters per second to the right. What is his resultant speed? Probably I should have asked what is his resultant velocity. Okay, now this is another type of explosion, not really an explosion, but a breakup of two masses that were together. So what we had is the astronaut with the anvil at rest, at least in their frame of reference, they are at rest. So their momentum before he threw the anvil is 0. And then we are going to have the astronaut and the anvil. The anvil is moving 17 meters per second towards the right. Let's make that my positive direction. So because my initial momentum is 0, my final momentum should be equal to 0. My after momentum should be equal to 0. But the anvil here has a momentum towards the right. So it has momentum of anvil is in this direction. So the astronaut should have an equal momentum in the opposite direction. So what's the momentum of the anvil? The momentum of the anvil is 1 kilogram times 17 meters per second, which is 17 kilogram meters per second. Now, the momentum of the astronaut then should be equal to minus 17 kilogram meters per second. So both of them will add up to 0. Okay, minus telling us he's going to be moving towards the left. Now, when we know the momentum of the astronaut, I can find his velocity. Velocity of the astronaut is the momentum of the astronaut over his mass. So in this case, that's going to be minus 17 kilogram meter per second divided by 67 kilograms. Okay, so in this case, that's going to be 17 divided by 67. I'm calculating it here on the side. Minus 0.25 meters per second. The minus tells me he's moving towards the left. Okay, let's work another question. We have a car is stopped for a traffic signal. When the light turns green, the car accelerates, increasing its speed from 0 to 5.2 meters per second in 0.832 seconds. What linear impulse the 70 kilogram passenger in the car experiences? Okay, it's missing an S there. Okay, impulse. What's impulse? Change in momentum. Impulse, remember, is final momentum minus initial momentum. So what's the initial momentum? The car and the passengers in the car were not moving. So the initial momentum is 0. What's the final momentum of this passenger? It's going to be the mass of the passenger times his velocity. Now, what's his velocity? It's going to be the same as the velocity of the car. So it's going to be 5.2 meters per second. So in this case, that gives us 70 kilograms times 5.2 meters per second. Minus 0, of course, for the initial momentum. Okay, so 70 times 5.2. So that gives us 364 kilogram meter per second. Okay, so this is the impulse of this guy. Notice we didn't use the time here. For impulse, you don't always need to use the time. You have two expressions. It's either change in momentum or average force times time. If the average force is not given, or if they are not asking us for the average force, we're not going to use the time. Now part B is asking for the average force that the passenger experiences in the car. Now then we have to consider the other expression for impulse that says it is the average force, average net force, times t. We are given the time, we just found the impulse. So the average force is going to be the impulse over the time. So in this case, that's going to be 364 kilogram meters per second over 0.832 seconds. So divided. So that gives us 437.5 newtons. So that's the force that this person had experienced due to the acceleration of the car, the average force he experienced. Now that's not bad, that's less than his weight, that's not a very uncomfortable force. Okay, let's work this other example. In a particular crash test, an automobile of 1,300 kilograms collides with a wall. The initial and final speeds of the automobile are VI minus 15 meters per second and VF 2.6 meters per second. Find the impulse caused by this collision. Okay, so this is our situation. Considering this as the positive direction, the car is moving initially in this direction at 15 meters per second, and then it's going to so this is again my wall. Of course, it's somewhat destroyed car, and it's going to move back this way at 2.6 meters per second. And they are asking us to find the impulse. So my initial momentum of the car is the mass of the car times its velocity. So in this case, that would be 1,300 kilograms times minus 15 meters per second. So 1,300 times minus 15 meters per second. So that would give me minus 19,500 kilogram meter per second. Now my final momentum is going to be the mass of the car times its velocity, and in this case it's going to be 1,300 kilogram times plus 2.6 meters per second. So 1,300 times 2.6. So that gives us plus 33,380 kilogram meters per second. Now, what's my impulse? Impulse is P final minus P initial. So in this case, that's going to be 3,380 minus 19,500. All of them in kilogram meter per second. So minus the minus gives me a plus, and the overall is going to be 22,880 kilogram meter per second. That's my impulse. Okay. Pay attention to the fact we had a minus minus, ended up giving us a bigger momentum, a bigger impulse than if the car would have stopped. Okay. Okay, one last example for this recording. What we have here, a car of mass 2,000 kilograms stopped at the traffic light, is struck by from the rear by a 1,200 kilogram car. The two cars become entangled. If the smaller car was moving at 25 meters per second before the collision, what is the velocity of the entangled cars after the collision? So this is, again, it's an inelastic collision. We have two masses kind of get entangled and move together, and we have energy lost into entangling the car and destroying them. So again, it's a conservation momentum problem before the collision and after the collision. So before the collision, what do we have? We have one car. Okay. Standing in the park, at the traffic light. Now, and we have this smaller car coming in towards it at 24 meters per second. That's a high speed, by the way. Okay, now, so what's my initial momentum? My momentum before the collision is going to be momentum of small car plus momentum of large car. Okay, momentum of small car is going to be the mass of the small car times its velocity of 24 meters per second plus 0, which is the momentum of the large car since it's not moving. So the overall momentum is 1200 times 24, which gives us 28,800 kilogram meters per second. Now, after the collision, the momentum should be the same, conservation of momentum, which means the masses, when they get entangled, they are going to move together with this momentum here, momentum after. Now the question is, what is the velocity of the cars after the entanglement? We know the momentum after, and the momentum after should be their combined mass, which is the mass of the small car plus the mass of the large car, times their combined velocity, the VC that we are trying to find. So that's going to be equal, their combined mass is 2000 plus 1200, so 3200 kilograms, times their combined velocity. So their combined velocity is going to be the overall momentum, 28,800 kilogram meter per second, over 3200 kilograms. Which gives us 9 meters per second.